Look up at the night sky. Thousands of stars shine down on us. Each one a distant sun, perhaps with its own planets orbiting it. But where did it all come from? How did this vast and intricate universe begin? The answer, as incredible as it may seem, is the Big Bang. Imagine a time before time itself. No space, no matter, just unimaginable energy, concentrated in a single point smaller than an atom. Then, in a fraction of a second, everything changed. That tiny point erupted with unimaginable force, an explosion of unimaginable scale. This was no ordinary explosion, however. This was the Big Bang. The Big Bang wasn't an explosion in space. It was the explosion of space itself. From that single, infinitely dense point, space began to expand. It's still expanding today, carrying galaxies further apart like raisins in a rising loaf of bread. But the Big Bang was more than the beginning of space. It was the beginning of time, of matter, of the laws of physics as we know them. It was the birth of our universe. The Big Bang Theory is the prevailing scientific model for the origin and evolution of the universe. It's not just a guess, though. It's backed up by decades of rigorous observations and scientific evidence. The theory states that the universe began from an extremely hot and dense state, some 13.8 billion years ago. Since then, the universe has been expanding and cooling. Imagine a balloon with dots drawn on it. As you inflate the balloon, the dots move further apart. That's a simplified way to picture the expanding universe. The Big Bang model doesn't tell us what caused the Big Bang itself. It describes what happened from that initial moment onward. Think of it like watching a movie. We can rewind the film to the first frame, but we don't know what happened before the camera started rolling. The Big Bang is a mind-boggling concept, but it's the best explanation we have for the universe we observe today. It's a testament to human curiosity and our quest to understand the cosmos. You might be wondering, if the Big Bang happened billions of years ago, how can we possibly know anything about it? Amazingly, the Big Bang left clues, echoes of that ancient event that still resonate through the cosmos. One of the most compelling pieces of evidence is the cosmic microwave background radiation. Imagine the faint glow of a fire, but stretched across the entire universe. This radiation, discovered in 1964, is the faintest of whispers, a thermal remnant of the Big Bang's intense heat. Another key piece of evidence is the redshift of distant galaxies. Just like the sound of a siren drops in pitch as it moves away, the light from distant galaxies is shifted towards the red end of the spectrum. This redshift indicates that the galaxies are moving away from us. The further away they are, the faster they seem to be receding. This observation supports the idea of an expanding universe, a universe that began from a single point. These echoes of the Big Bang, along with other evidence, provide strong support for the Big Bang theory. They allow us to peer back in time, to catch a glimpse of the universe in its infancy. Scientists have spent decades analyzing this cosmic data, using advanced telescopes and satellites. Tools like the Hubble Space Telescope and the Planck satellite have been crucial in mapping the cosmic microwave background. These instruments have provided us with detailed images and precise data, revealing the structure and composition of the early universe. Furthermore, they have allowed scientists to accurately measure the age of the universe, estimated to be around 13.8 billion years old. Each discovery brings us closer to understanding the origins and evolution of the cosmos. International collaboration and knowledge sharing have been instrumental in this journey of discovery. As we continue to explore the universe, each new piece of evidence helps us build a more complete picture of our cosmic origin. Future space missions and technological advancements promise to unveil even more secrets of the universe, taking us to new frontiers of knowledge. Thus, the echoes of the Big Bang not only speak to us of the past, but also guide us towards the future, illuminating the path towards new and exciting discoveries. Section 4. The first fleeting moments. The first moments after the Big Bang were a whirlwind of activity. The universe was incredibly hot and dense, a boiling cauldron of energy. In this extreme environment, even the fundamental forces of nature were unified. As the universe expanded and cooled, these forces separated, giving rise to the universe we know today. Within the first second, the universe had cooled enough for the first subatomic particles to form: quarks, electrons, and their antimatter counterparts. It was a chaotic dance of creation and annihilation, with particles constantly colliding and converting back into energy. As the universe continued to cool, quarks combined to form protons and neutrons, the building blocks of atomic nuclei. But the universe was still too hot for atoms as we know them to exist. Electrons moved freely, constantly interacting with photons, the particles of light. This early universe was a turbulent and fascinating place, a time of rapid change and incredible energy. Section 5. From Soup to Stars. As the universe continued to expand and cool, a crucial transition took place. This process was not instantaneous but took millions of years, during which the universe's temperature gradually decreased. Around 380,000 years after the Big Bang, the universe had cooled enough for electrons to be captured by atomic nuclei, forming the first atoms. This was a pivotal moment in cosmic history. This event is known as recombination. During recombination, electrons and protons combined to form hydrogen atoms, the simplest and most abundant element in the universe. With the formation of atoms, the universe became transparent to light. Before this, the universe was opaque, as photons could not travel freely. Photons, which had been constantly scattering off free electrons, were now free to travel unimpeded. This allowed light to travel great distances for the first time. These photons, released from the primordial plasma, constitute the cosmic microwave background radiation we observe today. This radiation is a relic from the early universe and provides a snapshot of what the universe looked like at that time. This era marked the beginning of the universe as we know it. It was a period of transformation and evolution that laid the groundwork for the formation of more complex structures. The universe was now a vast and expansive sea of gas, mostly hydrogen and helium, with slight variations in density. These variations were crucial for the future development of the cosmos. These variations, seeded by quantum fluctuations in the very early universe, would eventually give rise to the large-scale structures we observe today. Quantum fluctuations are tiny perturbations in the density of matter that occurred just after the Big Bang. Gravity began to work on these density fluctuations, pulling matter together into increasingly dense clumps. This process took millions of years and was fundamental to the formation of galaxies and clusters of galaxies. These clumps would eventually become the seeds of galaxies, the building blocks of the large-scale structure of the universe. Galaxies, in turn, would cluster together into groups and superclusters, forming the vast cosmic web we see today. Section 6. Islands in the Cosmos. Within the vast expanse of the early universe, gravity slowly sculpted clouds of hydrogen and helium gas. These clouds, scattered throughout the cosmos, were the fundamental building blocks of the universe. These clouds, bound by their own gravitational pull, began to collapse under their own weight. This process of gravitational collapse was the first step in the formation of more complex structures in the universe. As the gas compressed, it heated up, eventually reaching temperatures high enough to ignite nuclear fusion in their cores. Nuclear fusion is the process that powers stars, releasing tremendous amounts of energy. These newly ignited furnaces marked the birth of the first stars, colossal balls of plasma that flooded the surrounding space with light and heat. The light from these first stars illuminated the universe, which had until then been shrouded in darkness. These first stars were very different from the stars we see today. Not only were they more massive, but they also had a different chemical composition, as they formed from the most primordial elements. They were much more massive and short-lived, burning through their nuclear fuel at incredible rates. Due to their large mass, these stars lived short but intense lives, ending in spectacular explosions known as supernovae. The first stars clustered together, drawn by their mutual gravity, forming the first star clusters. These clusters were the first steps towards the formation of even larger structures in the universe. These clusters then merged and grew, eventually evolving into the majestic galaxies we observe today, vast islands of stars, gas, and dust scattered throughout the cosmos. Galaxies are the building blocks of the large-scale universe. Our own galaxy, the Milky Way, a spiral galaxy home to hundreds of billions of stars, is just one of billions of galaxies that populate the observable universe. Each of these galaxies contains its own collection of stars, planets, and other celestial objects, forming a vast and complex cosmic tapestry.